Hello everyone, I'm Jagannath and I am a senior scientist at Andrew Computational Solutions. Today I'll be presenting my work on multitask learning approach for automatic modulation and wireless signal classification. The agenda for today's talk would be I'll go over the motivation, discuss few state-of-the-art works. I will go over the proposed approach and the fine-tuning of the MTL model, and I will present the fine-tuned MTL performance, and then we'll conclude with the takeaways. This slide here shows the state-of-the-art work for generally in the modulation classification and signal classification realm. As you can see, most of the work focuses on single task modulation classification or signal classification, single task signal classification. Here we signal classification, by signal classification we mean wireless protocol or wireless standard classification, like if it is IEEE 802.11 or ZigBee, etc. As you can see, most of the works focuses on just a single task, whereas our work looks at modulation and signal classification, which is multiple tasks with a single model. And another distinction that you can see is that most of the works focuses either on communication or radar waveforms and not both at the same time. But our work focuses on radar and communication waveforms. This is to represent heterogeneous operational environment, as you will see in the upcoming slide where I will touch upon this again. Going over the motivation again, as discussed previously, the state-of-the-art approaches consider single task, which is either a modulation or signal classification, and that too with computationally demanding neural network architectures, which corresponds to expensive swap size, weight, and power demands for only one task. And they consider either radar or communication waveforms. Take, for example, the CBRS band, where the incumbent US Navy radar emissions must coexist with the commercial cellular. So considering both radar and communication waveforms will be essential in the coming days. And a tactical application for the signal intelligence, such signal intelligence models would be to enhance spectrum awareness, allowing soldiers to distinguish between friendly and hostile forces. And a major motivation is that low swap computational platforms are desired to minimize power and memory costs, such that such models, such AI models, can be supported on edge computational platforms, such as a radio with an FPGA or a CPU with very low processing power. Therefore, to address these requirements, we propose a lightweight multitask learning architecture such that it can achieve multiple tasks with a single model. In this slide, we'll talk about the need for such a multitask learning framework. And to the best of our knowledge, such a multitask learning framework is proposed for the first time to perform multiple signal characterization tasks, such as signal classification, modulation classification, etc. And why do we need multiple tasks? For example, wireless RF signals can take multiple modulation format. For example, the IEEE 802.11 AOFDM waveform can process multiple modulations such as BPSK, QPSK, and QAM modulations. Satellite communication signals can have MRA PSK modulations. Radar signals, namely airborne detection, airborne range, ground mapping, etc., adopts pulsed continuous wave modulation, but whereby they differ in their transmission parameters such as pulse repetition rate, pulse width, and carrier frequency. The same way, AM radio signals can carry either the double sideband or single sideband waveforms. Therefore, if the model is only classifying modulation classification, irrespective of the signal that is incident on the RF front end, let's say for example, if it is airborne detection or airborne range, it would say it's just a pulsed continuous wave modulation, and you wouldn't have any intelligence upon what that waveform was. So to have an additional intelligence, it would be beneficial to also include the wireless protocol or wireless standard of the incident waveform, such as not just the modulation classification, but also the signal type. In this slide, we go over the MTL model, the neural network architecture. So here, the single neural network architecture can perform multiple simultaneous tasks, and this is a Hyperparameter shared multitask learning model. And it performs inductive knowledge inductive knowledge transfer, such that it is trying the shared branch here. So you can see there's a shared branch and two task-specific branches. Performs knowledge transfer across the two tasks, such that the shared branch aims to learn a shared representation which is representative of the tasks here. So it can be n tasks, and the shared layer will be trying to learn a shared representation which is common among these tasks. And this way, it would improve the generalization capability of the model. And implicitly, it improves the learning efficiency and prediction accuracy on each task, as opposed to a single task learning model for that particular task. Therefore, we propose to take advantage of the mutual relation between the tasks in learning them with an MTL architecture. And additionally, Hyperparameter sharing significantly reduces the risk of overfitting by the order of number of tasks. So theoretically, if you have more tasks, it's going to even improve the performance, and it is going to have a better generalization capability, because it's trying to learn a shared representation which is common among these tasks. And such an application or such an advantage can be only exploited if these tasks are mutually related. So for example, you cannot use it to learn mutually exclusive tasks. These tasks has to be related, and if so, you can take advantage of the MTL model. Since modulation and signal classification are related tasks that can benefit from each other, we propose to use a Hyperparameter shared MTL model in learning these two tasks simultaneously with a single neural network architecture. And this equation here shows the overall task loss parameterized by the neural network parameters on the shared and task specific branches. And the overall task loss, LMTL, is a weighted sum of the task loss on the two tasks, which is the signal classification and modulation classification. So WM is a weight for assigned for this modulation, and WS would be the weight assigned to the signal classification. And theta SH, theta M, theta S represents the neural network parameters, the weights on the shared modulation and signal classification branches. So in training the MTL model, you are attempting to minimize the overall task loss such that you would arrive at a better neural network weights for the shared and task specific branches. That is shown here with the argument minimize the overall task loss. This slide here shows the dataset and evaluation setting. So we generated two sets of waveforms. One was in an additive white Gaussian noise, and the other was in a dynamic setting. And the table on the right shows the modulation classes and the signal classes and the application of each. So it has GFSK and the modulation and the signal classes Bluetooth, and pulsed continuous wave, and the various waveforms are the airborne detection, ground mapping, air-ground radars. And so those are the signal and modulation classes and their application. So in total for the AWGN, we have 9 modulation formats and 11 signal classes. For the dynamic setting, we have 6 modulation formats and 8 signal classes. And the table on the left shows the dynamic parameters that were used to that were used to generate the dynamic waveform dataset, which has 6 modulation formats and 8 signal classes, and it used the GNU radio dynamic channel model to introduce these propagation effects to it, such that it would simulate the hardware defects and propagation channel effects, such that if it was a Rayleigh or Ricean channel, whether the hardware had carrier frequency offset, sampling rate offsets, etc. So these are the parameters that are shown here in the table, and for both, we generated waveforms in a range of SNR ranging from -20 dB to 18 dB in steps of 2 dB. The dataset was the major contribution of this work is that the dataset was also released for public use, and it can be found in the GitHub link shared here. And additionally, these waveforms were generated at a sample rate of 10 megasamples per second. And the waveforms, each of the sample of the waveform is 128 samples long, so which means 128 complex IQ samples. And to pass it into the neural network, the I and Q samples, because neural networks cannot deal with complex samples, the I and Q samples were concatenated such that the 128 I and Q results in a vector of 256 samples. And to pass it into the CNN architecture that we have, it was reshaped into a 16 by 16 tensor. Now we'll talk about the extensive hyperparameter fine-tuning. So the answer that we are trying to find here is how dense and wide should the neural network be. So resource-constrained radio platforms require lightweight neural network models for implementation on FPGAs and, like I mentioned, low-power CPUs, etc. Dense neural network models for signal characterization, such as resource-heavy AlexNet and GoogleNet that were adopted by the authors of Reference 1, would seem impractical for support on such constrained computational platforms. Hence, rather than adopting dense computer vision models, we handcraft the MTL architecture to arrive at a lighter model. And then additionally, the network density has a direct effect on the learning efficiency and classification accuracy of the model. So in the upcoming slide, you would see this. We are studying the effect of varying number of neurons in each layer and varying number of layers, such that we are trying to answer how dense and wide should the network be. These graphs here shows the training on the signal classification and modulation classification, as well as the performance on varying SNRs. So as you can see, the legends here shows 8-4, for example, the 8-4-256, 4-256 shows that represents that in the shared branch we are using 8 convolution filters, and for all the filters we are using 3x3 kernel size, and 4 represents 4 and 256 indicates the number of convolutional filters in the task-specific branch and number of neurons in the fully connected layer of the task-specific branch. So 4 and 256 represents 4 convolution filters in the task-specific branch for both modulation and signal classification, and 256 neurons in the fully connected layer of the task-specific branch. So it shows the training and validation losses, training and validation accuracies in the training and for weighting epochs. As you can see, with the lighter model, that is with 8-4-256 and 4-256, the model learns faster because it's a lighter model. And whereas with the other denser architectures, it takes longer for it to learn. And C2SH implies we have an additional convolutional layer we're introducing an additional layer in the shared branch, which means we have an additional convolutional layer in the shared branch. C2SH MTL implies we have an additional convolutional layer in the shared branch and both task-specific branches to see if the model is going to benefit from having an additional layer, if it's going to extracting additional features of use for the performance. Now coming on to the class for weighting SNRs, the accuracy curve for weighting SNRs, we can see again here the model performs best with the lighter architecture, which has 8 convolutional filters in the shared branch, 4 convolutional filters in both modulation and signal classification, and 256 neurons in the fully connected layer. This is the fine-tuned MTL performance, that is the performance of the lighter architecture on both datasets, the RADCOM AWGN and RADCOM Dynamic. RADCOM implies radar and communication, and for both at 10 dB, these are the confusion matrices where we can see close to 99% performance for in classifying all those classes. And here is the overall performance of the fine-tuned MTL model on both datasets, and it can be seen that for the RADCOM AWGN, 98.58% modulation classification accuracy and 97.87% signal classification accuracy is achieved at 2 dB, which indicates the sensitivity of the model. And RADCOM Dynamic dataset here we are the model achieves 97.07% modulation classification and 90% signal classification accuracy at 2 dB. And with these experiments, we are trying to demonstrate the classification capability of the model on severely impaired waveforms under varying signal powers. The key takeaways here are that we tried to show that yes, multiple tasks can be achieved, such as modulation format and wireless protocol identification. It's an extensible architecture, which means it can seamlessly include additional tasks into it. And we demonstrated high sensitivity, which is above 90% accuracy at SNRs, about 2 dB for both tasks on the noise impaired AWGN as well as the propagation and hardware impaired dataset. And it was a lightweight implementation. The floating point version is 2.97 megabytes. And the additional contribution of this work was the open source dataset. We released the first of its kind radar and communication dataset for public use. It can be used for MTL, multitask learning, as well as single task modulation and signal classification. For future work, we have demonstrated performance over the air, but it was not part of this work. It will be part of our extended peer-reviewed article. It's still in the works, and we are planning to incorporate more number of classes and perform deep compression for implementation on embedded resource constrained platforms. So that concludes my talk. I'd be happy to take any questions. If you have any questions, please feel free to email me at ajagannath@androx.com, and you may also connect with me on LinkedIn. Thank you.